Hello, today we'll be doing Paul Hewitt's Conceptual Physics, Chapter 7 on momentum. So, we will harken back to something we talked about before, which was inertia, the property of matter to resist change. Do you remember that inertia, the more massive something is, the more matter there is, the more inertia it has, the more it resists change. Well, momentum is just a technical way to describe the inertia in motion. So when we say something has a lot of momentum, we're not usually talking about a parked truck that has no momentum at all. But if a truck is moving, we say that has a lot of momentum, even if it's not accelerating. If the truck is going 100 miles per hour and it's packed full of cinder blocks, that truck has a lot of momentum. So we have this intuitive understanding of momentum. That's most of where our intuitive understanding of inertia comes from, is inertia in motion. So for an example here, you know when something is coming at you with a lot of momentum that you want to get out of the way. So if you see a truck barreling toward you, you want to get out of the way. If you see a butterfly barreling toward you, you just stand there. You know when you see, remember that bag of concrete flying through the air toward you, you want to duck and get out of the way of that bag of concrete. When you see a pillow barreling toward you from your little brother throwing it, you just let it bounce off you. So, because you intuitively understand that that bag of concrete has lots of momentum, but that pillow has very little momentum. And you instinctively know that you don't want lots of momentum crashing into you. So we know, just intuitively, we know that momentum, now I'm going to use actually all physicists use a lowercase, this is supposed to be a lowercase p for momentum. Pressure, we like to use a capital P, so don't mix them up. This lesson is not on pressure, this lesson is on momentum. So lowercase p, momentum is proportional to mass. That means the bigger the mass, we know the bigger the momentum. The smaller the mass, like that fluffy pillow, the smaller the momentum. Because remember, momentum is inertia in motion. Okay, so what else can we intuitively grasp about momentum? Well, we know that velocity has something to do with momentum. Because if you ever go to a roller skating rink or an ice skating rink and you see your little sister skating towards you, and say she's going like, I don't know, about that fast, you might just stand there and let her bump into you. Now, if she's barreling across the ice, you're like, oh no, ouch. Because you know there will be more impact, there will be more momentum when she's going a lot faster. So we know, this is something else we can say about momentum, we can say we know that momentum is proportional to the velocity. The bigger the velocity, the bigger the momentum. So we take these two things that we know are true, and it turns out, this is our law, momentum is mass times velocity. That is what momentum is. It is mass times velocity. So a truck weighing many, 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 many pounds, loaded up with cinder blocks, going 70 miles an hour, has a huge amount of momentum. A little tiny Mini Cooper going 5 miles an hour has way less momentum. That little Mini Cooper going 70 miles an hour still has less momentum than that giant truck. The giant truck going 1 mile an hour, you can bring its momentum down somewhat. Just think about the more momentum something has, the more likely it can crash through a barrier. So imagine you've got a barrier and you're trying to ram it. Your best bet is either to get more mass or more velocity to be able to enough momentum to bust through that barrier. So the same barrier, say you've got a semi-truck that's just loaded up with cinder blocks, it's going to just go crashing through that barrier. The same barrier, if you've got a little Mini Cooper, no, don't pause it. And if you've got a little Mini Cooper, I know she's banging on the window with a baseball bat, it's going to be fine. Now you've got a little Mini Cooper and it's going along at the same velocity, but it's got so much less mass that it's not going to make it through the barrier. Okay, so when the momentum of an object changes, it's because a force was acted on it. This is what we call, we know what force is, and now we're going to talk about we're going to talk about impulse. So what is impulse? Okay, so let me just keep, so we don't forget the beautiful equation we just got about momentum. So what is impulse? Well, when a force acts on you, your question is how long? There's a really big difference between someone coming up and just pushing you once and stopping, or someone pushing you and running. So like if you're ever on like a scooter or a skateboard or whatever, you're playing with kids, and they ask you to give them a running push, sometimes even if it's a tall enough swing set, and a kid will request, no, don't just give me a push, give me a running push. And what that kid is asking for is more time that you're exerting that force. We know what force times time is impulse. And impulse is what changes momentum. So that force times that time. You know when you're driving the car, the longer, so the force is you stepping on the gas pedal, that's firing up all that chemical energy in the tank and propelling it forward. You know that the longer you step on that gas pedal, the faster, the more change in your momentum is going to happen. The faster you're going to speed up. The more your momentum is going to increase in that car. You know that just tapping on the gas pedal once for 1 second is not going to have the same effect as just holding down on it for 10 seconds. The same way the kid asking for a running push knows that in their little scooter or whatever they've got, that you just pushing it for 1 second is not going to have the same effect, the same increase in their momentum as when you go running and pushing on that scooter. No, she'll be okay. She'll be okay. I know, but Jenny's there with her. She's going to be fine. Okay, so how long you exert that force matters. So imagine you've got, not very big of a force, but say your time, you give it 10 seconds. So let's say we got a force of 5 newtons. You say you got a force of 5 newtons, and you're going to give it for 10 seconds. You're going to have an impulse of 50 kilogram meters per second. Now suppose you've got a huge force, like 100 newtons, but you only give it, let's say, half a second. You only apply it for half a second. Now you're going to actually end up with the same. Even though you have a much bigger force here, you only applied it for half a second. This is why if you want to maximize the momentum of an object, like a baseball or a soccer ball, you try to give it the biggest force you can and keep contact with it as long as you can. So when you're trying to hit a home run, you hit that ball as hard as you can, biggest force as you can, and you try to follow through with the swing. You try to follow through so that you're exerting force on that ball all the way through. So say if your force is, I don't know, let's just say 10 newtons, and the time, if you do it really fast, it's only going to be half a second. That's only an impulse of 5 kilogram meters per second. But now let's say that you follow through, you make contact with that ball for 5 seconds, it's 10 times bigger. Now you've got an impulse of 50 kilogram meters per second. Okay. So now we've got Ft is impulse. And remember, impulse is what changes momentum. So Ft is the change in momentum. This is actually just our old friend, F equals ma, rearranged a little bit, and I'll show you how. What's acceleration? Acceleration is the change in velocity over the change in time. Okay? Now we're going to multiply both sides of the equation by change in time. That cancels out. So now I've got F times the change in time.
Mom, the phone fell over.
Can you pick it up? Can you prop it? Okay, pause it. All right, this way. Okay, so we've got from here force times the amount of time, the change in time, mass times the change in velocity. Well, usually we assume the mass doesn't change, so I can move the little change thing out there. So force times change in time, and often when people say change in time, they just put in the time. You don't say from 0 seconds to 5 seconds, you just say 5 seconds. So we've got Ft is change in momentum, mv. Okay, so this is the next equation we can write up here. So we've got our definition of impulse, got the impulse equals the change in momentum. Okay. Now, let's talk about this for a little bit. So you already know, like we were talking about the example of you trying to hit the baseball bat, and hit the baseball as hard as you can. You already know to maximize the change in momentum of that baseball, you want to maximize the force and follow through as long as you can. Get the greatest force, the greatest impulse possible on that ball. Sweetie, so you want to increase the impact time, the time that you are, pushing that force through on that to make it go faster and faster. Okay, now we're going to flip it and think about it from the other angle. What happens, we already know how much momentum you had, the change in momentum. What happens when you've got a guy in a car that's going 70 miles an hour, okay? So we already know his mass. Oh, let's say he weighs 200 pounds, okay? So we've got a 200-pound guy, and he's doing...
Video started.
Okay, so we've got this momentum that the guy initially has. We've got 14,000 horrible units of it. And the momentum that he has at the end, when his car is stopped, is 0 horrible units of it. So to go from here to here, we know this is fixed. The change in momentum is fixed. The change in momentum will be his initial momentum, 14,000. Let's just make, I don't know, what should we do for my awful new unit system? 14,000, I'm just do a star, okay? 14,000, these are weird units of momentum, minus, we have change in, 0, his final weird momentum. So we know that the total change in momentum equals force times time. The total will be, let's say, well, the total here is 14,000 stars will be 14,000 weird unit will be in this impulse. So the question is, if he goes from 14,000 weird units to 0 weird units of momentum in 1 second, we know that the force on him will be 14,000 units of force, right? Because if the time is 1 second, he's got 14,000 units of force on him.
I'm about to pause it because he is coming.
No, don't pause it. Just keep playing it.
Okay.
So now you've got 14,000 units on this side. That was his change in momentum. Will be 14,000 units of force times that 1 second. Now suppose the guy stops in 100 seconds. Okay? So this is fixed. His change in momentum is fixed. You got 14,000, but instead of the time only being 1 second and there being 14,000 units of force, 14,000 units of force. Now you've got, he stops over the course of 100 seconds, and now you've only got 140 units of force.
You just did.
Pause it.
I'm paused it.
So now if he stops over 100 seconds, he only has 140 units of force on him instead of that 14,000 units of force, because we know it has to be this much change in momentum. Now let's say he goes over 1,000 seconds, he breaks over 1,000 seconds, now he's just going to have a gentle little 14 units of force on him. Now you see this when they say don't brake too quickly. When you're driving in the car and you've got a set amount of momentum, say you're doing 60 miles an hour, or let's say 45 miles an hour on a surface street, you got a set amount of momentum. When you try to slam on the brakes, you can feel that lurch. The force exerted on you is quite intense. When you slowly step on the brake, so you slowly divvy out that deceleration, that changing your momentum to 0. When you do it slowly, it's much gentler on you. So I did this the hard way once. I was driving with somebody who I think had back problems, and I slammed on my brake, and it made her back hurt because the forces exerted on her were much, much greater than if I gently stepped on the brake. So after that, I tried to be better about making sure I step on the brake gently so I don't exert more force on the people in the car. Okay, so another example that we're going to look at is when you've got a set amount of momentum. So say you jump off of something really tall. So you jump off the roof, not quite the roof, jump off a table. So you have a set amount of momentum because you have a set, you have a velocity, you have a mass, and you know that you're trying to take your momentum to 0, landing on the ground. So in this case, you will bend your knees as you fall, as Sarah Grace would like to demonstrate for us. I'll shift it around. Sarah, do it again, baby. Sarah Grace will demonstrate for us what you do when you jump. Do you see how she, do that again. I'll focus this time. So we'll focus on her landing. So she's going to jump, and you will see she bends her knees. Why does she bend her knees? To make that fall spread out. Here, sweetie, is this proper again? To make that fall, that momentum, she's making the force on her knees, the force on her legs, the force on her is spread out over time. It's the same concept as when as an airbag. You've got all that momentum, and you're gonna smash it straight into the front of your car, and that airbag is trying to spread out the time so that the force can be smaller. So when Sarah was bending her knees as she jumped, what she was doing was, for a set amount of momentum that she had coming down, about to hit the floor, she was making the time be longer so that her force could be smaller. Try it. If you jump, don't try it, but if you do try it, if you jump off a table and keep your knees locked, you're gonna hurt. You're gonna feel it. Because if you lock your knees and you just smack the little bit of time, that same jumping off the table, you will have experience a very strong force. Like when I slammed on the brakes and you feel it, a very strong force on you, versus if you make it over a lot of time. This is why the whole, conundrum of you're in a car and you're gonna either hit a wall or a haystack, and you want to hit the haystack. Like suppose it was a massive haystack. Say that haystack actually had the same mass as the wall. You want to hit the haystack. Why? Because in a haystack, you can make it go much longer time. It's like bending your knees, or like the airbag. When your head makes contact with the front of your car in a car crash, you want that airbag, what the airbag does is it makes the contact take much longer, more time, and so that same force, the same momentum that you're trying to go, from 70 miles an hour to 0, whatever it was in that car crash, you're spreading it out over time so that the force will be less. Another example of this is we used to live in an apartment with a carpeted floor, and my kids threw things, we dropped things, we had glass dishes, and they never broke. We lived there for 5 years, and they never broke. And then we finally got a house, and we have this very nice, shiny, hard floor that's easy to clean. And we broke something like 27 dishes in 3 years because they're different. More than that. Well, okay, more than that. I stopped counting after 27. Okay, so, and the reason is because the carpet, here you've got the same amount of, those dishes have the same amount of momentum, right? They're falling off the table. Kids are bumping them off the table. Same amount of momentum. That same dishes, okay, same Corelle dishes, they're falling off the table. And in the apartment, when they landed on the carpet, it took more time because it had more, we think of it as give, although carpet has more give, but that
it was harder to clean.
Yeah, it was harder to clean now. The impact takes up more time. They finish that impact, and while it's using up that time, it's distributing that force. So for the same amount of momentum for that bowl falling off the table, the time of the impact was longer, and the force could be smaller. Because remember, we're studying it has to equal this number on this side. What happens when it's hitting our nice shiny concrete floors is you got the same momentum, the same dish falling from the same height, it's the same amount of momentum.
It couldn't be the same dish because the dish broke.
Well, it's from the same company, the same Corelle bowls. But in this situation, you have the time, that little split second that it hits that hard floor, it has to still equal this. So it experiences a much greater force in that much tinier bit of time. Another way that we think about this is in boxing, I think, or in punching sports. They talk about riding the punch. And that's as you're getting punched in the face, you want to move backward with the punch. What you're doing here is you are spreading out the momentum of that punch over more time, and therefore your face is experiencing less force. What you don't want to do is bring your head into that punch. That will make the time be much shorter, and the force you experience on your head will be much greater. Same principle when the first lesson of horse riding is teaching you how to fall, or I think a lot of sports actually, the first lesson is how to fall. And one of the ways you're supposed to fall is keep your body super relaxed and spread it out as much as possible. There's also the pressure, force of area thing going on, but there's also time. You're trying to spread out that you hitting the ground in as much time as possible, because for the same momentum of your body hurtling from horse height or whatever height, for the same set momentum of your body flying through the air, you're trying to dissipate that force in a much longer time and therefore have a smaller force on your body versus just smack. A harder force on your body. Okay, so now we've covered how impulse, the force times the time, is the change in momentum. And now we're going to talk about bouncing balls and bouncing things that bounce and the change in their momentum. So remember, momentum is a vector because it has a velocity. It's not your mass times your speed, it's your mass times your velocity. Momentum is a vector, has a direction. So you say, okay, they've got, these many kilogram meters per second in the north direction. The truck is going north. The truck has, 1,000 kilogram meters per second north. Okay, so one of the things we'll notice with bouncing is that if something bounces, so its momentum is going this way, let's say it's a ball, so momentum is going this way, so we'll say down, its momentum is down, let's say it's 5 kilograms and it's going 10 meters per second. So it's 50 kilogram meters a second of momentum going down, okay? Now let's say that it hits the floor, okay? Bam. What's its momentum now? So momentum is 0 because its velocity is 0. And remember, even though it's still 5 kilograms times 0, 5 kilograms times 0. Yep, this is the non-bouncing ball. So we say, what has the change in momentum been for this guy? The change in momentum for this guy has been 50 kilogram meters per second minus 0 kilogram meters per second. So overall, the change in momentum for this guy is 50 kilogram meters per second. Now what happens in the situation where the ball is falling, same ball, but it's going to bounce. So it hits the ground and it comes back up. That's a different situation though. But okay, it's springy, whatever. So now it bounces back up. So its initial momentum was 50 kilogram meters per second down, and now its momentum is 50 kilogram meters per second up. Okay, let's make the down one negative because we've got a little axis here. So let's imagine that things going this way are negative, things going this way are positive. Okay, so it had been 50 kilogram per meters down, up per second, down, and now it's up. So now you see the overall difference in its momentum is 100 kilogram meters per second. You can see that because look, its initial one, or you know what, let's make the one going down positive. Makes it look prettier. And the one coming up negative, okay, on the axis. So its initial one, if you look, is 50 kilogram meters per second. That's its initial momentum. Minus, because we're doing change, negative 50 kilogram meters per second. So you see the two negatives, remember 2 negatives make a positive. So you end up with the difference is 100 kilogram meters per second. This is like the way you go from having $1 in your pocket to being $1 in debt. There's $2. You spent $2. It's the same principle. Okay. Say if you only have $1 in your pocket, you go to the store, you buy something that's $2. You borrowed $1 from the store. You borrowed $1 from your brother. Now you have negative $1. So we don't say, oh well, now you spent your $1. The difference. The thing cost $1. No, the thing cost $2. So this is the same idea here. When it bounces, that's double the change in momentum. What does that mean? That means that was double the impulse down here. So for example, if something bounces off someone's head, you know just from looking that hurt twice as much as if something bounced and just stuck the same object. Obviously there's different objects and how they stuck. Anyway, so that is bouncing gives you twice the impulse. The book had a cool story about how a guy used this in a water wheel to figure out how to make the water wheel turn faster. Instead of having paddles, he had cups. and it sent the water shooting back up, and this gave twice the impulse. Because remember, if it changes the momentum completely, it didn't just come down and stop. The momentum came down, shot back up. So now you've got twice the impulse, and that pushing that water wheel twice as hard. So that was a pretty cool touch about the water wheel. Okay, now we're going to talk about conservation of momentum. So with conservation of momentum, the momentum is conserved if there's no outside forces. The momentum is conserved in that system. The key to remember here is in that system. So you've got a gun, a loaded gun with a bullet in it, and it shoots the bullet. Okay, so the bullet is now going, I don't know, I think in meters and hundreds. Anyway, the bullet is now moving, so this bullet has momentum, the bullet's mass has momentum, and this gun has recoil. It's recoiling back in the guy's hand. Well, what's going on here? This, if you multiply the velocity of the bullet times the mass of the bullet, you will get a number. Let's say you get 500, it's probably more than that. 500, or is it, I don't know, kilogram meters per second. And say, you know, if that's the momentum of the bullet, you know, because here, the momentum of it before it fired was 0. The momentum was 0 of the system. This is the system. So this tells you that when you fire, you already know, if you know the mass of the gun, you can even calculate the velocity of the recoil. Because you know, remember they're vectors. Remember conservation of momentum, you can add up momentum because they're vectors. So we're not saying that conservation of momentum means that the bullet can't shoot. The bullet shoots, but the gun recoils. So if you take the velocity, remember this is the velocity in the negative direction, think about it like a number line. This is the velocity in the positive direction. If you multiply the mass of the gun times the velocity in the negative direction, and the velocity of the bullet in the positive direction times that mass, these guys will cancel each other. You will get a number of, like, if you multiply the mass of the gun times the velocity of the gun, which is going to be in the negative direction, you end up with negative 500 kilogram meters per second to perfectly balance these out. So 500 kilogram meters per second, take away, negative 500 kilogram meters per second, you're going to end up with 0. Because when you add them together, these are, sorry, not take away, when you add them together, because you're adding it together in the system. Okay, so
it's already 16
here,
minutes.
sorry, we'll finish up, sweetie. So elastic collision. So elastic collisions is when the things aren't stuck to each other at the end of the collision. So think of 2 billiard balls. They hit each other and go flying off. That's an elastic collision. An inelastic collision is if the 2 billiard balls are stuck to each other. So a lot of physics books love to do this with train cars, and they'll show like an inelastic collision is when the train car like hitches, from ramming on the track, and they're now moving together. So for the conservation of momentum, say you've got a one little train car on the track moving. Let's say this is 500 kilogram train car, and it's going 2 meters per second. And then there's a little train car who's not moving at all. So we know that his momentum. So this guy's momentum is 1,000 kilogram meters per second. But this guy isn't moving at all. So we know his momentum is 0, because his mass might be 500 kilograms. But now his velocity is 0. So his momentum is 0. This guy's momentum is 0. So this guy's initial momentum is this guy's initial momentum is 0. Now they smack into each other and are moving. It's an inelastic collision, so they stick to each other. The little thingies stick to each other. So now you've got, they're stuck to each other, and they're both moving along the track. So remember, this guy was going this direction. So now these guys together are moving along the track. And you say, well, how fast are they going now? We can actually figure that out, because for the conservation of momentum, we said initially the system, we add up all the different momentums of 0 plus 1,000 kilogram meters per second. So that tells us that the momentum in this system, with the law of the conservation of momentum, has to still be 1,000 kilogram meters per second. And because we know that, and we know that now we've got, before here, we only have 500 kilograms. Remember this now, which is to 0. But this now we know we have 1,000 kilograms, so we know exactly how fast they're going. They're going 1 meter per second. We have 1,000 kilograms. And we know they're going 1 meter per second in this direction. Elastic collision is if they bounced away from each other, and then you would have to subtract 1 because their directions are going in different directions. Okay, so now let us talk about the fact that it's not all train cars hitting each other. As you know from car crashes and things like that, because velocity is a vector, when we're not talking a railroad track, we're usually working with more than one direction. So for an example, or let's say two ice skaters crashing into each other. It's less violent. Two ice skaters crashing into each other, okay? So we're looking from heaven. We're looking down from the sky. And we see this little dude going along, skating along in a line this way. And this girl skating along this way. And they smack into each other. Bam. And we can already predict they're going to start sliding together. It's an inelastic collision. They got stuck. They're going to be sliding together in that direction. Well, how do we know this? Because of vector addition. We see he was this, she was that. We know what direction they're going to be going because of vector addition. Remember, we're looking from the sky. These are their heads. We're looking at their heads. Say he's blonde, she has dark hair. So we can see. We know with vector addition which direction they'll go. Likewise, two cars smash into each other. Say it's an inelastic collision. They get stuck. We know the resulting, he was going this way, he was going this way. The resulting velocity, y, we can just do it this way and say, okay, that's the direction that they're going in. Okay, so now in real life, car crashes, they don't just keep zooming that direction because of friction. As you're scraping across the pavement, all that heat, all that stuff, the friction is giving an impulse, force times time, the force of the friction over the time that they're scraping across the pavement, and will bring them to a halt. If you had a ship crash in outer space, so they would hit each other, there's no friction, they would just keep on moving on their combined vector. If you had two ships crash into each other, they would just keep moving on their combined vector until they get pulled into a gravity well of a planet or something. Okay, so I think we have covered pretty much everything in that chapter. So see you next week.